bring to start recording. Yeah, sorry about the delay in getting the video from Tuesday's class posted. I used to upload the video for class right after class, which is kind of problematic for this class, because then I'd be here really, really late. Okay, we're already here very, very late, but it would be even worse. So I'm trying to get in the habit of doing it the following morning, but it's taking some effort to make that routine. Okay, now for homework 1, the Matlab assignment, not many people have submitted it yet. I think out of a total of 24 people in the class, I think only 4 or 5 have turned it in. So I hope to see it soon from the rest of you, simply because there will be other due dates coming for other assignments. So I don't want to have a situation where if things get pushed back, late penalties pile up, or something ends up just falling off the edge, just because we run out of semester. So as I mentioned last time, you do have some leeway on this assignment. It is not required to successfully complete all of the problems to get 100%, because the total number of points available is 116, but your grade is still determined out of 100. And also, this entire assignment counts for 3% of your grade, and problems such as the one where you determine the day of a week, even though it's more involved, is not worth any more points than the one where you're writing a script to add 2 matrices. So these are things to keep in mind. So like I said, I'm not enforcing a late penalty, but just as a recommendation, please do not, for your own sake, please do not take too much longer in getting that in. Okay. All right. So the plan for today is to finish section 2.1 on error analysis. So the next week will be floating point arithmetic. So after this section, you should be able to do the problems, the explorations from section 2.1, which is what makes up homework 2. All right. So last time I introduced various types of errors that are all related. Yes, thank you. Okay. Yeah, that's better. Okay. Absolute error, relative error, and then forward and backward error, so really we have 4 types of error, because you can have all the different combinations of forward, backward, absolute, relative. One comment I want to make about backward error. So I'm going to be updating these notes and then that I started last time, and so tomorrow notes that cover the whole week will be posted. And there are those strange question marks again. Okay. Okay. To compute backward error for a specific case. So the idea is, suppose you are given x, so like a specific x value. I'm going to call it x naught to make clear that it's some fixed specific x value. Sorry, having difficulty in the typing department. And your function f of x, and approximation, which I've been referring to as f hat of x. So the forward error would be f hat of x minus f of x. And for simplicity, I'm going to use absolute errors in this case. But for relative error, you're just taking that and dividing by the exact value. Okay. So what is the what's the backward again and again absolute backward error? Okay, well that's defined to be x hat minus x, where f hat of x is equal to, like I said, the exact solution of a nearby problem. So to compute backward error of any kind, you need this x hat. X, and how do you get an x hat? It's the value of x, that is the x value that satisfies this equation. So the left side, like, so you're given, I should fill in my subscripts here. Okay. Again, because this is an example of like a specific numbers given for x. Wait. Okay. So what this means is you need to solve the equation hat f of x naught is equal to f of for x naught hat. Okay. Now, because you're given x naught, you're given f, into which you can plug in x naught, and you're also given a function and you're given this function f hat. So because you were given all of these, the left side of this equation, that's something you can compute. You can just plug and chug away on that, and you have that. It's x naught hat that's the only unknown in here. So so what you're given specific functions for f, and therefore f hat, then you can solve this equation to get x naught hat. So as an example, one of the homework problems, f of x is cosine, and then f hat of x is an approximation of cosine that's given by a Taylor polynomial. For example, 1 minus x squared over 2 is the second degree Taylor polynomial for cosine. Now, I'm going to refer you to some examples in the book. So for more information, see examples 2.1.6, 2.1.7 on page 50. Okay, so those are examples that I put in there to illustrate the process of obtaining backward error. Okay, so, and I'm pointing this out because, like I said, there's some problems in homework 2, like 2.1.5 that specifically deals with obtaining a backward error. So you're following what's in those examples to do the homework problem. I should mention that when I taught this class 2 years ago, so I'm working with a draft of this book. It wasn't yet submitted for publication. And because of certain things that students were having difficulties with, I added some examples, in particular chapter 2, to help with those students with these problems. So hopefully that ends up helping you too. Okay. Now, what I'm hoping will also help is I'm going to work an example that illustrates several of the things that I talked about on Tuesday. Forward error, backward error, and the condition number. Okay. So example illustrating forward and backward error, and condition number. Okay. And we'll deal with both absolute and relative. Okay. So I'm going to work with a pretty simple function here, because really all I'm trying to do is just illustrate the concepts that we have here. So f of x is just going to be, say, x cubed. And then my x, my input, is just going to be, let's see, 4. Okay, and let's make this up as I go along. And then my, so a backward error is given by, so what, in this case, in this example, we do not know the precise backward error. All we know is that x is accurate up to a certain level. So there's a certain accuracy level that we know of for f. For example, x comes from a measurement, and we have an upper bound on the error in that measurement. So we know that the difference between x hat and x is 0.1. Okay, so this gives us, so we get this from what we know about the accuracy of whatever measurements we're taking. Okay. So what are we trying to do here? Use a condition number to estimate forward error, which is f of x hat minus f of x. Okay. And in both the absolute and relative sense. Okay. All right, I'm going to move this onto a new page. Okay. So what we have here, as far as backward error is concerned, what I've just so if we have the absolute backward error, so that is less than or equal to 0.1, just from what's up here. And then the relative for backward error, again phrased as an upper bound. What would that be? So the information needed for that is written here. What do we do to get from the absolute error to the relative error? Divide by what? By what? Which is? Yeah, we're dividing by 4. Yeah, so, yeah, it's going to be x hat minus x over x. So that's going to be bounded by 0.025. Okay. All right. Now, as I mentioned at the end of last time, the absolute condition number of function f of x is approximately the derivative. Okay. Now, that was worked out here because it's just a difference of y's over difference in x's. Now, what about the relative condition number? So I'd be taking this y hat minus y and dividing by y, so there would be a y in the denominator. And then x hat minus x, the absolute backward error, is supposed to be divided by x, but that's already in the denominator, so there's an x in the numerator. So if you worked all this out, if you substituted relative errors here instead of the absolute errors, I'll just jump to the punchline here. The relative condition number, a way to estimate that for a given function, is x f prime of x divided by f of x. Okay. So now we can go ahead and use these estimates to estimate the condition number for this function, f of x equals x cubed, and that will lead us to estimates of the forward error. Okay, so with that in mind, for fx equals x cubed, the absolute condition number, I'll just abbreviate here, kappa absolute, and we'll use absolute value here. Absolute condition number, it will be a function of x. Yeah, thank you for remembering your Cal 1. Well, actually, don't need absolute value in this case, but generally we do. Okay. And then relative condition number. So that's going to be, so we have x and then 3x squared over x cubed. So that simplifies quite a bit. Actually, it's 3, because we have x cubed upstairs, x cubed downstairs. So it's interesting that the relative condition number turns out to be a constant. So, in fact, what we would see for f of x being any power of x, you're going to have x to the n down below, you have x up top, you have n x to the n minus 1 as a derivative. All the x's will cancel, so the relative condition number of x to the n is always n. Okay. So from these condition numbers, we can estimate. So estimates of forward error. So in the absolute case, okay, and again, it's just an approximation. We're only trying to get in the ballpark. We never expect to get exact error, but some notion of order of magnitude is helpful. Okay, so what we have here is we have absolute. So what we do is we take the absolute backward error, 0.1, and then times the absolute condition number. But I need to fill in the value of x. So, okay, so x is equal to 4. So what we get is 4.8. So what this means is that so in fact, the absolute error can be quite large compared to the so the absolute forward error can be quite large compared to the absolute backward error. So we see a fair amount of amplification because of that condition number, in this case being equal to 48. So what's happening is x is changing by only 0.1. So the value of f of x is changing by roughly 4.8. Okay. Now what about the relative? Same idea. So it's always going to be backward error estimate times condition number estimate. So same thing here. So the relative backward error is 0.025 times the relative condition number, 3. So that would be 0.075. Okay. So now this is saying that the relative backward error is not amplified that much. And in general, we can expect to see this kind of discrepancy in terms of how error is magnified by the function because of differences in the absolute condition number versus the relative condition number. So to show you why that is, let's fill in some specific numbers and see what happens. Because x is varying by at most 0.1 in either direction. So let's do that. Let's consider a specific value of x hat that's within that range. Okay, so I have let x hat equal 4.1. And I could go plus or minus. Let's go plus in this case. So then we have f of x hat is going to be, okay. All right, so 68.921. Okay. Whereas, all right, so compared to x equal 4 and f of x equals 64. Okay. So what we need to do now is, now we have specific numbers here, we can compute actual forward errors, both absolute and relative. So let's take a look at that. So the absolute forward error, that's going to be 68.921 minus 64. So that's just going to be 4.921. Okay, compared to the absolute error estimate of 4.8. So that was certainly in the ballpark. Okay. By contrast, the relative forward error, so that's just going to be the same, the absolute forward error divided by the exact value, which is 64. Okay, so, all right, so 0.0769. Again, very much in the ballpark of our error estimate, which was 0.075. And now for the specific numbers, we can see why that is, why the absolute forward error seems so much larger. It's just because of the exact value being larger, being 64. So if the exact value had been around 1, then we would not see this discrepancy between the absolute and relative error. But the main thing I want to show you is, so this is what we see is error propagation. That you have some knowledge of the error in the input, and then from this knowledge of how a function behaves, which only depends on your measured x value, then just by multiplying these, backward error times condition number gives us an estimate of the error in the output, the forward error. Okay. Now, this is why it can be very frustrating when, for example, one of my other classes that I teach is Math 102 online. So for those problems, so in that class, the students often have to provide an answer that's accurate to within 2 decimal places. And so what's happening is if you're performing several steps, punching numbers into a calculator and taking one result to the next step and so on. And I often have to tell them, if 2 decimal places is required in the final answer, don't round to 2 decimal places, your intermediate results. Wait and retain more decimal places. Wait to round until the end, and that's because in those problems where they're plugging numbers into exponential functions and so forth, or power or polynomials, there's a lot of error propagation going on. They have some erroneous value and that's erroneous due to rounding or the limited precision of our calculator. And if they're not careful about that, their final answer could be thrown off. So they could have worked out the problem correctly in terms of the actual mathematical method being carried out, but rounding alone could end up delivering a wrong answer, and then they're wondering why. So it's something that can be pretty insidious. Is this error propagation? Because we think, this input value is accurate to a certain degree, and so we'll have that kind of accuracy preserved through whatever computation is performed on that value. And that's not true at all. We have to understand how whatever black boxes or numbers are being plugged into can have the effect of amplifying whatever error is already there. So error that is extremely small at first can grow substantially. Okay. So questions about what happened in this example? All right. Now, okay, a quick comment I want to make about another thing I brought up at the end of last time. That is conditioning versus stability. Now, as I mentioned last time, conditioning is a property of a problem, the underlying problem you're trying to solve, whereas stability is a property of the algorithm that you're choosing to solve it. In many cases, there's more than one option there. So, an example of where this can come into play. So example, solving A x is equal to b. In other words, a system of linear equations. So A is your matrix, B is your given right-hand side, and X is your unknown, the solution that you're seeking. So you learned how to do this in Math 326. So using Gaussian elimination, or what you may know it as, row operations. Now, those of you, well, hopefully by now you have taken linear algebra. What are the different row operations you perform on a matrix when solving this kind of system? There are 3. Scaling. That's the least interesting one, but yes. What are the other 2? Yeah, adding a multiple of one row to another, which is the most important one. And what's the last one? What? Yes, interchanging rows. Okay. So suppose a matrix. So suppose the matrix A is well conditioned. Okay. So in other words, the problem itself is a good problem. Unfortunately, it takes too much background material to explain what the conditioning of a matrix is. It's the same notion of condition number that I've been giving you, but for a matrix, it can be made more specific. But the point is, a small change in B will not lead to a large change in a solution X. So we have a well-conditioned matrix, but suppose a 1-1 entry of A is extremely small. Let's say 10 to the minus 10. Okay. Now, if you think about how you would solve this system using the techniques that you were taught in Math 326, so you can solve this system without interchanging the first row with another row. Because now, the thing is, if this element was exactly 0, then to perform Gaussian elimination, you must make a row swap. But because it's non-zero, it's more of a guideline than a rule. All right, so you can solve this, and this is called Gaussian elimination without pivoting. So in other words, you only interchange rows in the situation where if you don't, you're going to divide by exactly 0. So in that case, you have no choice. But otherwise, you're just going to leave a row stand. This is actually proven to be an unstable algorithm. So while technically it does work, it does not work very well. In other words, there could be a lot of error propagation. So because this element is so small, and assuming all the other elements are of a more reasonable magnitude, your computed solution, like with a computer with limited precision arithmetic, can actually still be inaccurate, even though the problem is well conditioned. So what do you do instead? Use Gaussian elimination with pivoting, so that you make sure your pivot element that's used for determining which multiple of row you subtract from another row is as large as possible. In other words, because this one is so small, we would swap the first row of some other row, even though we don't absolutely have to. That is proven to be stable. So the idea is, or the bottom line, if you have a well-conditioned problem and a stable algorithm for solving it, can expect an accurate answer. But if you're missing either one of these things, that's where trouble arises. If a problem is well-conditioned, that's a better situation. You can always adjust your algorithm to make it more numerically stable. In numerical linear algebra in particular, which is something that I cover more in depth in the second course, but that's where the better examples come from. There are a lot of cases where an algorithm that actually is taught in one of our courses, like to work out on paper, but a computer performing it, such as Gaussian elimination, turns out to be numerically unstable. So some adjustment is made to it. And that's something you wouldn't learn about in one of those classes, because for working out on paper, it's not really necessary. But for when a computer's doing a heavy lifting, it is needed. Okay. Whereas if you have an ill-conditioned problem, that's a lot harder to deal with, because simply changing methods or tweaking methods may not be enough. Okay. It's not something that can't be resolved, but it's certainly a lot more difficult. Okay. So I just want to put that out there about what it means for an algorithm to be stable as opposed to conditioning of a problem. So it's very important to keep in mind what term applies to what. Okay. Now, for the remainder of a section, we're going to look at convergence. So many algorithms in numerical analysis are iterative, meaning they generate a sequence of approximations that I'll label AN, that converges to the exact solution of whatever problem it is as n goes to infinity. Okay. Okay. Now, so the thing is, in a non-numerical class, like for example, you deal with sequences in Cal 3. So if a question in a class like that is, given some sequence, does the sequence converge to a limit at all? And in certain simple cases, you may be able to determine what that limit is. But a lot of cases you can't. You can only determine convergence or non-convergence, or convergence or divergence. But in numerical analysis, it's not. Okay. Oh, dang it. It's not just about whether AN converges, but how rapidly it converges. And the reason is, there may be, and in some cases we will see, multiple methods, iterative methods, that will produce a sequence of approximations that can be guaranteed to converge to the exact value if you take infinitely number of iterations. But with numerical algorithms, efficiency matters. So if we have an algorithm that can converge to a solution in like 1/10 the number of iterations of another, then guess which algorithm is going to be used? So we study the rate of convergence of such sequences. Okay, so some notation for discussing convergence. All right, so we have big O notation. So what we say is some sequence. Okay. Some sequence AN is big O of Bn if the following is true for n sufficiently large. Absolute AN is less than or equal to some constant times Bn for some constant C that is independent of n. So it's a way to concisely describe the growth or decay rate of some sequence. What is a sequence? A sequence is a function of the natural numbers. So how does that sequence behave? Does it grow to infinity or decay to zero as n goes to infinity? Okay. All right, so that's big O notation. And an example of that, let's suppose that AN is defined to be, let's see, I'll just make something up here. Okay. Now, okay. So what we have is absolute value of AN is less than or equal to, okay, so I have this. Well, I'm going to use a triangle inequality and work on these terms separately. Okay, so here I do need absolute value. Okay. Now, for hello, stop that. Okay. But for n greater than or equal to 1, we have an is less than or equal to. So what I can do is I can multiply this by n squared. And this term I can multiply by n. And we still have a 5n squared. In other words, so I have a misplaced symbol here. Sorry, it's driving me nuts again. Okay. Here I have 3 and 2n. I'm allowed to multiply, since I have a less than or equal to here, I'm allowed to multiply these terms by anything that makes them bigger. And then the less than or equal to can still hold. I'm already assuming n is greater than or equal to 1. So if a number is less than or equal to 3, it's certainly less than or equal to 3n squared. And I'm doing that because it allows me to combine all these terms. So I have 10n squared. So our conclusion is that an is equal to big O of n squared. With a constant c from a definition equal to 10. Because that works. And then also, it only has to hold for n sufficiently large. And even just assuming that n is greater or equal to 1 is enough to prove that this holds and establish that an is order n squared. So this captures the growth rate of my sequence. When we have positive powers, if we have a negative power, then it's a decay rate. It's decaying to 0. Alrighty. Now, so as far as rate of convergence is concerned, all right. Can be expressed in terms of big O notation. All right. So if we have a sequence that converges, so in other words, we know it does. So an converges to A. Then the rate of convergence of an to A is expressed in big O notation, order Bn, if we have the following. An minus A. Now an is converging to A, therefore an minus A is converging to 0. So if that difference between the sequence and its limit is order big O of Bn. Okay. So that's how we determine the rate of convergence of a sequence. Okay. All right. So I'm going to work out an example here. As soon as I have my pages in order. Okay. All right. So to define my sequence to be, all right, so I have 2n squared plus 4n. So I think doing a fraction so it doesn't show up until I type in the whole thing. N squared plus 2n plus 1. Okay. Now, for a sequence like this, there is there's a trick to very quickly come up with a limit of the sequence as n goes to infinity. And it's taught in calculus. What is it? I'm sorry, I really cannot hear you. Oh, well, you can use L'Hopital's rule, but there's a way it's even quicker than that. Yeah, divide top and bottom by n squared. Really, you can look at, because the degree is the same, you can look at the coefficients of the leading terms. And the ratio of the coefficients is 2. So the limit is 2. Yeah, you can use L'Hopital's rule. You can divide top and bottom by the highest power, which is n squared. Those are all ways to get the limit. But the quickest way, when the degree is the same, above and below, just look at the ratio coefficients. And I'm doing that part quickly because this problem is not about getting the limit like in calculus. It's, once we know the limit, what is the rate of convergence? So now what we want to look at is, what is the rate of convergence? So we examine this fraction. Okay, so it's going to be the same fraction minus 2. Where'd it go? Oh, I've got a brace here. Okay, so we need to see how rapidly does this go to 0. It's going to, because we know it goes to 0 because 2 is the limit. But what about like, it's going to go to 0 like some simpler function that clearly goes to 0, and we want the simplest function possible. So what we're going to do is, well, how would I simplify this? Use your algebra. What? It's just going to be 0, right? Oh, well, it goes to 0, but we want to see get a handle on how rapidly it goes to 0. So if I want to simplify this fraction to get it, because it's not apparent just from looking at this.
Minus 2 over the n squared plus 2 plus 1.
Yeah, so common denominator is the technical term for it.
Yeah.
That I fear that people have forgotten. Okay, so I'm going to copy this fraction here. Okay. But I need the same thing above and below. Okay, so now we have a common denominator. So I'm going to take this 2 and distribute it through here. So up top I'm going to have 2n squared plus 4n plus 2. So this is going to work out nicely because we have lots of terms that are going to cancel. So all that's left is equal to minus 2 over n squared plus 2n plus 1. Okay. Now, how can I simplify the denominator? What is that? Yes, you recognize that as a perfect square. Okay. So we want a simpler function that's big O of this. So, and the thing is, okay, I'll go to a new line here. Actually, I need to go to a new page. Okay. I need the absolute value of this fraction here. Okay. Now, I can make any. I want this to be, see what this is less than or equal to, a function simpler than this, and I can make this, perform any manipulation on this that makes it bigger, because I'm only looking for an upper bound. Now, to make a fraction bigger, you can make the denominator smaller. So I can say that this is less than or equal to 2 over n squared. Now, if this was a minus 1, I could not do that. I'd have to be more careful. I can still get some sort of bound, but this right here, so I can say that this is big O of n to the minus 2. Okay, so this right here, n to the minus 2 or 1 over n squared, that is the rate of convergence.
That's why it's worst case.
Yes. In fact, I can say a little more about that in a moment. Rate of convergence. Okay. Okay, so when you have something that is going to 0, it is the function that is decaying the slowest that determines. So yeah, if I had several terms here with several negative powers of n, it's the one that's least negative. In other words, the power that's closest to 0 is what determines the rate of convergence. Because what you could show is that slowest decaying power of n is larger than all those other powers that decay faster, as long as you pick the right constant. Okay, so power that is least negative, or it's closest to 0. Closest to 0 determines rate. But you have to think about what functions, other functions besides polynomials or rational functions. For example, take 1 over n. So 1 over n decays to 0 more slowly than 1 over n squared or 1 over any higher power of n. But can anyone think of a function like 1 over a function, so 1 over something that also is going to go to 0, but will go to 0 more slowly than 1 over n? There's more than one right answer. What? Well, not n squared, because n squared will go to 0. Yeah.
One over the sine of n?
That oscillates forever, won't converge.
1 over n minus 1?
Very slightly so. But in terms of like growth, those actually decay to 0 at a very similar rate because the power is the same.
That will go slower?
Yeah.
1 over square root of n?
Yes, is one example. So a power of n that is positive, but still less than 1. So, and I could go further. I go n to the 0.001. Now, what type of function would so 1 over it would decay even slower than that? That's still in that category. Logarithmic functions. So a logarithmic function grows more slowly than any power of n, no matter how small. So therefore 1 over it will decay to 0 more slowly.
Wasn't there like something weird about e and log in the case of big O notation just because of transcendental?
As in like they should not be used or something, or not used, or.
No, it's just something I've never understood for page structures.
Oh, okay. Yeah, I'm not sure about that. Yeah, because we like to express polynomials in or algorithm complexity usually in polynomial time. Or so many algorithms that are not that require something exponential. Okay. Okay. Now, there's actually another type of convergence to illustrate. So not just for n going to infinity, but also so another type of wait, need to put some space here. Okay. So another type of convergence, instead of a sequence of a continuous function f of h as h goes to 0. This is going to be important later this semester for derivatives and integrals, because in both cases, you're dealing with h referring to some sort of spacing, whereas the spacing goes to 0, you get the exact derivative or integral, but we have to use a positive spacing. So we want to see, so the error can be expressed in terms of this spacing, and what is the rate of convergence of that error to 0. So we have similar notions of big O notation. Big O notation, same meaning, that we have f of h is bounded by some constant. Well, I should say almost the same meaning. So f of h is bounded by a constant times some other function g of h for h sufficiently small. That's the only difference. Means that f of h is big O of g of h. So we have to change that because before we had n going to infinity. Here we have h going to 0. Intuitively, you can think of h as being playing a role of like 1 over n. We still need to have its kind of upper bound, but because we're going to 0, we want h sufficiently small, close to 0, as opposed to n being sufficiently large, going towards infinity. Okay. Rate of convergence. So f of h. Okay. Converges some value f naught. You can think of it as f of 0, but it may be a function where you can't plug in h equals 0 because maybe there's a divide by 0, like for a derivative, a certain number of limits. So it converges to whatever value f naught, that's the limit, with rate of convergence, that's big O of g of h, if the difference between the function and the limit has that big O. Okay. So now I'm going to illustrate that. Okay. Let's see. Okay. So I'm going to let f of h equal, let's see, sine h minus h over h. Okay, I'm going to make this bigger. Okay. So we'd want the limit of this as h goes to 0. Now, okay. It turns out the limit is 0. Okay, I'm going to put parentheses around this. Okay. Now, the reason why you can see that it goes to 0, I could rewrite this fraction as sine h over h minus 1. Now, but we have this limit. So this part, sine h over h, that's going to 1. Here we have minus 1, so the whole expression is going to 0. So what we want to do here is understand what the rate of convergence is. Okay. Now here's how we can do that. Use a Taylor polynomial. So what we have here, so fond memories of Cal 3 for you. The first few terms of the Taylor series, I'll just use sign h. So the first term is h, and then we have minus h cubed over 6, or 3 factorial. And then I could keep going, but actually what I'm going to do is, okay, sine c, sorry, I'll come back in a second, times h to the 5th over 120. Okay. Oh, actually, no, I don't want to do that. It should be h to the 4th. Oh, and actually, that should not be sine. Wait. Okay, so 3/4 derivative. Okay, that actually is sine. Okay. Now, I want to explain to you where. So these first two terms may be familiar to you. This term, perhaps not. I want to explain where it came from, because we need to work with Taylor's theorem and its full form. Taylor polynomial with remainder. So what we have here is f of x equals f of x naught plus f prime of x naught plus f double prime of x naught over 2 times x minus x naught squared, and so on. So if I keep going, so the last term in the nth degree Taylor polynomial is nth derivative of x naught over n factorial, okay, times x minus x naught to the n. All right, so what we have here, everything up to this point is a polynomial degree n. That is the nth degree Taylor polynomial. But what follows, like the gap, the error between this polynomial and the true f of x, is the remainder. So that remainder, which may not have been dealt with much in Cal 3, although it should have been. So I have n plus 1 factorial downstairs. I have x minus x naught to the n plus 1 over here to the right. And then in the numerator, I have the n plus first derivative evaluated at some unknown point, which I'll call C or squiggly. So that is an unknown point between x and x naught. So the best we can hope for is maybe get an upper bound in this. Like if we know how large this n plus first derivative can be between x and x naught, which are both known, then we get a handle on the size of this error, which is something we will deal with from time to time throughout this course, and also the next one for those of you who are up for it. So what happened here? This h comes from I'm taking the Taylor expansion of sine around around 0. So it's a Maclaurin series. And I have, so the 0 degree term is 0. This is the first degree term, which gives me h. This is the third degree term. So if I stop at n equal 3, then this term will give me the remainder. So that's going to give me h minus 0 to the 4th power over 4 factorial. And then I have a fourth derivative of sine, which is sine, at an unknown point. So that's my remainder term. So I just want to explain where that comes from. Okay. So the idea is, to get the rate of convergence, we substitute this Taylor polynomial in here, and then we'll simplify as much as we can. Now what we can see as soon as we substitute this in, we have a h, which is going to cancel with this h. And then we're going to have these two other terms. And we're going to have 1 power of h cancel. So by substituting Taylor polynomial and remainder into f of h, and really it's f of h minus its limit, but the limit is 0, we obtain the following after simplifying as much as we can. Okay, so I need this. So I need to deduct 1 power of h, because we divided by h. Okay, and okay, there should be a minus in front for this term. Okay, so simplifying as much as we can, this is what we get. And as a result, we get big O of h squared. And the reason why it's big O of h squared is, remember, h is going to 0. When you take small numbers and square them, they're only going to get smaller. And then if you cube them, they get smaller still. And that means that the h squared part is going to be decaying to 0 more slowly than h cubed. So one thing that sequences, as n goes to infinity, and functions as h goes to 0 have in common is that the power of n for sequences or h for functions that matters in terms of determining a rate of convergence. It's the power that is closest to 0 that tells you in a multi-term expression which one gives you the rate of convergence. Okay. All right, so zero determines rate. Okay. Alrighty. Questions about this example? Okay. All right, and so I actually have a similar example. Okay, involving a cosine that's worked out in the text using the same idea using Taylor series. All right. Now, we have some time left. I do have another example that I can discuss of convergence as h goes to 0, but I wondered if some of you might find it more pressing if you have any questions about homework that you'd like to ask instead. Whether it's homework 1 or I know there's a couple of you who have started looking at homework 2. That'll be fine too. So any homework questions at all? Okay. I should know this after 10 years. No one ever asked questions on homework in class. Although there should be more asking of questions on homework outside of class. Because I understand the hang-up of asking in class, but that same excuse doesn't apply to shooting me an email, for instance, or whatever. Okay. Now, Now, so this example, which relates to one of the problems I've assigned, deals with approximation of derivatives. Okay, so I have this formula. Approximation of a second derivative. Okay, so this actually comes from a definition of a derivative applied twice, because definition of derivative, you have f of x plus h minus f of x over h, and you can let h be positive or negative to get two different approximations. You plug those in to take a derivative of that, and you get this. Okay. Now, so what I want to do is, so the question is, how rapidly does this approximation converge to f double prime of x naught as h, the spacing h, goes to 0? Wait, where's my arrow? Okay. Okay, now here again, we're going to look at Taylor series. Because what we can do is we can express f of x naught plus h and f of x naught minus h using Taylor approximation. So first for f of x naught plus h, so we have f of x naught plus f prime of x naught times h plus f double prime, which is what we're after, h squared, and then h cubed, and then the last term will be the remainder. So 1 over 4 factorial f fourth derivative. Now remember, with f with an exponent that's in parentheses, that means higher order derivative. Typically used for derivatives of order 4 or higher or 3 or higher, because once you have so many primes, it can be hard to read. So that is evaluated at an unknown point, squiggly. I'm actually going to call it squiggly 1 for the plus case. And all of that is times h to the 4th. So this is my Taylor approximation with remainder. For f of x naught plus h. And then I can do the same with f of x naught minus h. Now it'll be very easy to do after doing the first one, because all you're doing is you're replacing h with minus h. So every alternating terms are going to change sign. And the in the last term here, because this unknown point is between x naught and x naught plus h. This unknown point, which I must give a different name, is between x naught minus h and x naught. It's a different unknown point, so that's why I have to call it something else. Although it should not be in the superscript. Let me fix that. Okay, need to put that there. Okay, I probably have a ton of LaTeX errors in this, but I'll fix those later, as long as you can see what's on the screen. So now what I can do is I can take these Taylor expansions and substitute into here. And notice, like here, both of these have an f of x naught. This one. And I have a minus 2 f of x naught here. So all the f of x naughts are going to cancel. Also, notice both f of x naught plus h, f of x naught minus h have a plus sign. These have opposite signs. So they're going to cancel also. So all of this is going to go away. And then these two terms will add together to give me f double prime of x naught h squared, but that divides by h squared. So I'll get f of f double prime of x naught. These terms will cancel, and then these terms will still have. Okay, so what I'll end up having is, okay, actually, I should be more careful about this. It's only an approximation. It's not exact. Okay. Now, so if I take this approximation and simplify everything as much as I can, okay, so that's what I have on my left side. And then, so this works out to f double prime of x naught plus 1/24 times h squared. Okay. Times the fourth derivative at these unknown points. So I'll put these in here. Okay. So fourth derivative evaluated at c1 and at c2. Okay. So this after simplifying everything as much as possible. Okay. Now, I'd like to try to simplify this as much as I can. And to do that, I'm actually going to break up this 1/24 fraction here. So I'm going to make this 1/24 a 12, and then I'm going to put a separate factor of 1/2. Now, so my thinking here is, okay, to simplify, we use the intermediate value theorem. Extremely important theorem in numerical analysis in various places. And it's taught in Cal 1, and this is anyone's chance to dazzle me by telling me what it is.
I can try. For a function that is continuous, differentiable in an interval AB, f of A can be estimated by the formula f of B minus f of A over minus A.
What theorem is he actually trying to quote?
The integrated value theorem.
No. You're closer. You're far closer to a different theorem that's also taught in Cal 1. Anyone think what that might be? No? Anybody? Mean value theorem. Okay. The intermediate value theorem says that if f is continuous, only has to be continuous on a closed interval AB, then f assumes every value between f of A and f of B at some point in AB. So this is very important, for instance, for solving equations. For example, if f of A and f of B have opposite signs, then f has to be equal to 0 somewhere in the interval. So in other words, it's used to prove existence of a solution of an equation. And that's something we use toward the end of a semester. Okay. Now, here we're going to use it for a different purpose. So this is not part of the theorem, but how we're going to use it here, including their average. So the average of f of A and f of B is necessarily between f of A and f of B. So it's an intermediate value. So So we could say here that, so the reason why I separated this 1/2 out here is, so 1/2 times this sum here is the average of these two. So, therefore, there exists some point xc between xc1 and xc2, and therefore also between x0 minus h and x0 plus h, such that, so now I'm going to copy this and update it. Okay, so this average I can replace with just the fourth derivative at some, again, unknown point that I'll just call squiggly. Okay. Actually, I'm going to move this to a new page. Okay. All right. Now, typically with these kind of formulas, the convention is actually opposite to how I defined error before, like definition of absolute and relative error, where we say the exact is equal to the approximation plus the error. So I'm going to rearrange this. All right, so we say f double prime x naught is equal to this approximation, and then let me clean this up here, minus this error. So this got moved to the other side. So this expression here, minus h squared over 12 times the fourth derivative at an unknown point, that expression is the error in this approximation. And this is just a convention for like approximate derivative approximate integral methods. We conclude that this approximation is big O of h squared. So because the error is order h squared. Now, if I continued Taylor expansion, there would have been more powers of h, but those would have been higher powers. It's a power of h closest to 0 that determines the rate of convergence. So in other words, if I use this to approximate a derivative, I cut h by a factor of 10, the error should decrease by a factor of roughly 100. So it's quite accurate for a second derivative. All right. So questions about what was done here? I'm going to, since I've already talked about, I've done part of a Cal 1 review. The mean value theorem, which is also important in numerical analysis, states that if f is continuous on AB, differentiable on AB, then we have this fraction, f of b minus f of a, or b minus a, is equal to f prime of c for some point c in this interval. Okay. I actually have not taught Cal 1 since 2011, but that theorem is still off the top of my head, not only because I deal with math all day, every day, but because I've had still, even though I haven't not taught Cal 1, I've still used this theorem from time to time. Played a prominent role in the book, for instance. Okay, so in the last few minutes, I'm going to set the stage for, this concludes discussion of section 2.1. I'm going to use the last 5 minutes to set the stage for section 2.2 by using this approximation in Matlab. Okay. I'll post this diary. So I'm going to set x naught equal to, let's say, to my function will be the exponential. Well, I want to refer to it as f. So that's why I'm doing this. My h, I'll let, say, 0.1. Now, the second derivative of the exponential is what? Yeah, it's exponential. So the exact value is going to be is that e squared. So let's do this. F of x naught plus h minus 2 times f of x naught plus f of x naught minus h all over h squared. Okay, that's pretty good. I need to label that. That's my approximation. And let's get the error. So relative error. Exact minus approximation divided by exact. Now let's see how we did. All right, 10 to the minus 4, not bad. Because h was not that small, 0.1. So now let's try h equal 0.01. And I will do the same thing. And look at the error again. Notice the error really did decrease by a factor of 100 when I shrunk h by a factor of 10. So this numerical evidence of it, this really is a second order accurate approximation where the error is big O of h squared. And I could keep going, of course. Okay, if I do this again, compute the error again. All right, so now it's getting kind of boring. So let's do this. I'm going to make h super small. Let's just go right to the exact answer and drive this error to 0. Let's say 10 to the minus 14th. And I'll compute my approximation. And let's look at the error one more time. It should be tiny, right? No. It's awful. It's the worst approximation in recorded history. And next week we will find out why. So, well, some might already know why, but that's the theme for next week. Okay.